This video will cover the dehydration of aldol products. The dehydration of, or removal of water from, the aldol product is one of the ways in which we can push the aldol reaction towards products. Remember that the aldol reaction is an equilibrium that tends to favor the reactants. The product of the aldol reaction is an alcohol that can be dehydrated to form an alkene. This dehydration reaction can be catalyzed by acid or base in the presence of heat. The dehydrated aldol product is very stable, and therefore its formation is very favorable, meaning that the dehydration equilibrium lies very far to the right. This is one of the ways in which we can push the aldol reaction to the right, because if the dehydration reaction occurs spontaneously, that will use up the aldol product, pushing the aldol equilibrium towards products as well. The reason that the dehydrated aldol product is so stable is because we form a highly substituted alkene. Remember that more substituted alkenes are more stable. And even more importantly, this alkene is conjugated. Conjugated double bonds are alternating single and double bonds. Conjugated double bonds are very stable because they consist of delocalized pi electrons. Additionally, they consist of multiple resonance contributors and therefore are very stable. The dehydrated aldol product is very stable, meaning that the second equilibrium is very favorable. This uses up the aldol product and, according to Le Chatelier's principle, causes the first equilibrium to be pushed towards products. One more important thing to note about the dehydration of aldol products is that since it can be carried out under acid catalysis or base catalysis, we can run both the aldol and the dehydration in the same reaction, just by adding heat. In other words, the aldol followed by the dehydration can be carried out in a single step under acid or base catalysis in the presence of heat. Now let's look at the mechanism. The mechanism for the acid-catalyzed dehydration of aldol products is a review. This mechanism is the same as the one we previously talked about with the dehydration of alcohols under acidic conditions. In the first step of the mechanism, the alcohol is protonated. This converts the hydroxyl group to water, making it a good leaving group. Next, water leaves to form the carbocation. In the final step of the mechanism, deprotonation occurs to produce the alkene. Notice that the alkene is formed at the most substituted position and in conjugation with the ketone double bond. The most substituted conjugated double bond will be the most stable product. Next, we will consider the base-catalyzed dehydration mechanism. In the first step of the mechanism, base deprotonates at the alpha position to form the enolate. This enolate ion is resonance stabilized. In the final step of the mechanism, the ketone reforms to create the conjugated double bond and kicking off the hydroxide leaving group to form the dehydrated aldol product. Notice that these two mechanisms are very similar. The same steps happen, but in different orders. In the base-catalyzed dehydration reaction, the proton is abstracted first, followed by the loss of a leaving group to form the alkene. In the acid-catalyzed mechanism, these two steps happen in the reverse order. First, the leaving group, water, leaves, followed by proton abstraction to form the alkene. Also notice that the intermediates in the acid-catalyzed dehydration are positively charged, while the intermediates in the base-catalyzed dehydration are negatively charged. Identifying the similarities and differences between these two mechanisms will help you understand the mechanisms and learn them.